Hey everyone, this is Michael from Barton Musical Circuits. This is a schematic walkthrough for the Synched Resonator module. Briefly, we have an input signal that is going to get compared to some threshold voltages by these two comparators. These comparators then turn on a pair of gated oscillator modules using CMOS NOR gates. These have their own outputs, the OS1 down up there and the OS2 down here. Those outputs then get mixed together for our wet output, which then gets mixed with our input signal by the blend and output over here to the output. So to go into more detail with this, our input we're expecting to see a VCO output like a triangle wave or something. That is going to get sent to this buffer, and the AC1 and AC2 things here, these go to a toggle switch. So when this switch is closed, signal is going to ignore any of this, and it's just going to see 100K resistor to ground. And if there's any DC offset to your input signal, that's going to be preserved, which that's something that you might add to the signal in order to create interesting like kind of harmonics where it's oscillating more on one side than the other. Or it's engaging the oscillators more on one side than the other. But when the switch is open, instead, it's going to go through this cap that'll remove any DC offset from it. And we have 100Ks on both sides of the cap, so that way you're not going to have any like big popping sounds whenever you plug something in, since the cap will be discharged on both sides. The output of this buffer is going to our two comparators over here. And it's going to the positive of one and the negative of other. So one of these is an inverting comparator and one is a non-inverting comparator. And then the output's also going to go way over here to our blend knob too. But so the threshold voltages for those inverting and non-inverting comparators, those are coming from over here, the threshold knob, which is this one, and then the threshold control voltage, which is input here at TH and then gets attenuated by the TCV pot. So the threshold knob's creating a variable voltage from +12 to -12, while our threshold CV might just be like 0 to 5 volts if you're coming from kind of your standard envelope generator. And so to compensate for that, when these get mixed together, our threshold voltage goes through 100K and our TCV only goes through a 10K. And then also, it's only a 56K resistor in the feedback path on this inverting mixing stage. It's making it so that the threshold knob, its output is getting cut in half, while the CV's output is getting multiplied by 5, basically. This gives our threshold voltage for the inverting comparator down here, and then that gets inverted to get our voltage for the non-inverting comparator. So the result is you end up having two thresholds at the bottom and then at the top of your voltage range. So if this was 0 volts here, if you input 5 volts here, you'd have a -5 and a +5 thresholds. And then if you input 3, you'd have +3 and -3. And so that's going to set it so that these comparators are turning off and on. The outputs go through these diodes, so these will only pass voltage that's above 0 volts, because they're being sent to gates that have 100K resistors to ground. And the two oscillator circuits are identical, so I'm just going to look at this one while we're going through the schematic. So you can just assume the other one's the same. So what we've got here is we've got two NOR gates, the CD4001, not OR. So an OR gate is one which has a positive output whenever either of its inputs go positive. And a not OR gate just does the opposite. Whenever either of the inputs are positive, we have a negative output. And when they're both negative, that's the only time we have a positive output. And one of the tricks you can do with a not OR gate is you can just ground one of the inputs, which then just turns it into an inverter. And that's what we're doing with our comparators. When the comparators are off, they're looking at our input signal, these comparators back here. That is when it's off and it's that that is going to have this gate here go down to ground, and this gate is going to turn into just a regular inverter. But when that comparator turns on, we're going to set up a state where the output can never, ever go to a high voltage. It's stuck at 0 volts. So when these are both set up as inverters, what we've got set up here is a way for this cap to charge and discharge in a way that's going to create an oscillation. Through our frequency knob here in this 2.2K resistor, we've got a path for this inverter to start charging or discharging this capacitor. And it's always going to want to be at an opposite phase of whatever the output of this second gate is here. And then we have this other resistor here that is going to help linearize the change in voltage on this first inverter here. This is a CMOS inverter circuit that's been used a bunch. I got exposed to it in Don Lancaster's CMOS cookbook, and I'm sure there's another video somewhere online that explains this in better detail, or you can also try it out in Falstad to see how the current works. But we basically, as you turn the resistance down here, this is going to charge faster. Resistance up here, it'll charge slower, and we're controlling our frequency that way. The output gets sent to the oscillator output through a decoupling cap. We use a tin UF cap here because that allows us to get the really low frequencies out, because the oscillators can go down to 10 hertz. And then the outputs are mixed together. This top one goes straight into the mixer, and this bottom one goes through an inverter first. And we do that so that way the two oscillators are going to be out of phase with each other, because they're reacting to different phases of our input signal. When they get mixed together, we want them to also be out of phase, so that way you're creating a signal that has a little bit of like polar movement to it. And then when it gets mixed back in with our clean signal, that's also going to give us a better it'll be a more interesting output than if they were both going in the same phase. So anyways, those get mixed together and then reduce their 10K input resistors with a 4.7K feedback resistor. So that's halving them. So instead of it being a 10 volt swing, it's going to be 5 volt swings on each side, since we're mixing these two waveforms together. And then the output of that gets sent to the blend knob. So the blend knob has 200K input resistors, and then those go to the two sides of the pot, and the wiper is grounded. So as you're turning the pot, you're basically grounding out one side more than the other. And you can ground one side out completely, or in the middle, they're both grounded out equally. And then those signals then get mixed together by this inverting gain stage here at the end. And this has a 200K resistor in the feedback, because you're always going to be attenuating something. That's some makeup gain from the blend pot there. And then finally, this goes to the output through a 1K resistor. I don't know if I mentioned it earlier, but the CD4001 is positive voltage only. So it connects to our 12 volt supply and ground, which is why we had to put the diodes in here and make it so that it was only passing positive voltage to it. We didn't want to give it a voltage outside of its voltage range. But yeah, that's this module. Thank you so much for watching. Hope you learned something, and hope I explained it okay.